discuss about logic gates. So far we have studied the gates of OR gate, AND gate, NOT gate. So that was the basic, they were the basic gates, and we have also discussed their Boolean expressions. Now we will continue our discussion and go further on the NOR gate, NAND gate, exclusive OR gate and the exclusive NOR gate. So now NOR gate. So what is a NOR gate? Basically it's a OR gate, combination of OR gate and NOT gate. So NOT and OR, we have taken N and N from NOT and OR from OR gate, and it gives NOR gate. So NOR gate is basically it's a OR gate with the output inverted. Means if we invert the output of a OR gate, then that will make a NOR gate. So means like this, you can understand this is the symbol for the OR gate and this is the symbol for the NOT gate. So basically NOR gate is a OR gate followed by a NOT gate. So this is the symbol for the NOR gate. We have A, B, C as inputs and output as Y. This bubbled structure, that is the circle, it indicates the inverted, whatever we have given, that is inverted after this bubbled. So we have OR gate, output of OR gate is going through this bubbled structure, so the output will be inverted. If we put this bubbled structure here, this circle here after C, this means that C will be inverted at the input of the OR gate. Since we have already discussed about NOT gate and OR gate, so we can realize these gates by using diodes of the OR gate and the transistor of the NOT gate. You can very easily realize just putting the output of OR gate to the input of the NOT gate, which we have studied already. So the truth table of NOR gate we will be discussing here. So we will discuss 3 input NOR gate. So A, B, C are the inputs and Y is the output. Let us see. It is very interesting to see if we have inputs 0, 0, 0, that is A, B, C all are 0. If suppose if it were a OR gate, then that would have been 0. Since it is inverted for NOR gate, so this will be in one state. For OR gate, if any of the input is in one state, output will be in 1. Since in NOR gate the output is inverted, so if any of the input is in one state, output will be 0. So by looking at this truth table, we can generalize a formula, or we can generalize a statement for the NOR gate. So what is the generalization? The output will be low. Here we see that for all entries except the first one, we are getting 0, which is the low state. So the output will be low, that is will be 0 if any of the input is high. Just see, if any of the input is high, output will be low. Here you see only C is high even though output is low. Here B is high even though output is low. Here all 3 are high, the output is low. So the output will be low if any of the inputs is high. Any or more, we can say, if one or more than one inputs are high. This was about the NOR gate. Now we will discuss the NAND gate. Again, the NAND gate is the combination of AND and NOT. So AND we have taken from NOT and A and D we have taken from AND gate, so it makes it as a NAND gate. So this is an AND gate with the output inverted. Again, we have a AND gate whose output is inverted. So that makes it as a NAND gate. So now this is the symbol, means we can just according to our definition, we have 3 input AND gate which is followed by a NOT gate. So basically this is a AND gate followed by a NOT gate. So this is the output of a NAND gate. So all these NAND gate and NOR gate, they have 2 inputs or more than 2 inputs. So this is the symbol for the NAND gate. We have A, B, C as input, and this is again we have a bubbled structure or the circle here, which gives the inverted output of this AND gate. So we should remember that NAND gate is a basically AND gate followed by a NOT gate. If we implement the output of the AND gate to the input of the transistorized input of the NOT gate, we will be getting output as a NAND gate. So it is not necessary to show the circuit. You can easily realize, you can easily make it just by putting the input the output of AND gate to the input of NOT gate. Now the truth table of NAND gate, again as I told, that truth table is to verify any gate. So that's why we are discussing at each step the truth table of each gate. So now we have again 3 inputs, means we may take also 2 inputs. So if we take 2 inputs, then we will have only 4 combinations, 0 0 0 1 1 0 and 1 1. Since we are taking 3, so we would have 2 to the power of 3, that is 8 possible combinations of A, B, C. So again here we see, if we take 0 0 0, so if it were a AND gate, it would have been 0, but since its output of NAND gate is complement of the AND gate, therefore it would be in one state. So we see for all entries we will be getting one state. For last row here, if we take 1 1 1, that is A, B, C all are 1, A, B all inputs are 1, in that condition for AND gate it would be 1, but for NAND gate it will be the inverted of AND gate, therefore we will be getting 0. Again, can you make a generalization, a generalized statement for this NAND gate? So the generalized statement will be, we see that for these entries, for first 7 rows we are getting 1. So what is the condition to get 1? We can get 1 if any of the input is 0. Means here you see only C is 0, even though we are getting 1. Here you see B is 0, even though we are getting 1. Here you see only A is 1, then we are getting 1. So the generalized statement could be, the output of a NAND gate will be high, will be in one state if any of the input is low. We can, if we have a NAND gate of 10 inputs, so if any of them is 0, then output will 100% be in high state. So and output will be in 0 state if all the inputs are in one state. So this statement can be generalized for a NAND gate, that any of the input is low, output will certainly be in high state. Now we will study the XOR gate, which we have already told, that is exclusive OR gate. What is exclusive OR gate? What is the importance of this XOR gate? We will see now. So the exclusive OR gate, we can define it as the output of a 2-input XOR gate is high if one and only one input is high. It's very important to note that if one and only one, means if we have 2 inputs and one is high and one is low, or first is low, second is high, then only the output will be high. That is, means if the inputs are not equal, and not equal means they can either, means as I told that in digital system we can take only either 0 or 1. The first is 0, the second is 1, or the first is 1, second is 0, then the output will be high. Otherwise, it will be low. So this is the symbol for XOR gate, and this is the truth table. A and B are the inputs and Y is the output. So if we take A and B 0, then output will be 0 by the definition. It will be in one state only and only when if both the inputs are not equal, and both the inputs are equal, then output will be 0. You see, in the first row we have 0 0, means both the inputs are same, then output will be 0, and the fourth row, if we see both the inputs are identical, then output will be in 0 state. So, and we can construct from, we have this truth table, then we can construct the output. You see, output I have just written y is equal to a bar b plus a b bar. How can we write it? You see, for constructing output from the truth table, we have to see the output status. We have to enter all the inputs for those outputs where we are getting one state. So here we are getting one state here and here. So as I told, if we assume a as 1, then a bar will be 0. So this 0 will stand for a bar, means a complement, and this b will stand for b is equal to 1. So this will correspond to a bar b, and this will correspond to a b bar. So we have a bar b plus a b bar. So we can construct output from the truth table also. So now how can we realize this y, means the output of XOR gate, exclusive OR gate, using AND gate and OR gate? As I told that AND OR gates are basically they are the basic building blocks. Here you see, so we have to realize a bar b plus a b bar for output y. So we take a and b, two inputs, and we for one AND gate we apply a and the second input as b bar. Now we want to take b bar, means we have to invert our input before implementing on the AND gate. So we put here a circle or the bubbled structure. So here b bar is implemented at this AND gate. So now on second AND gate we can give a bar b by just implementing a and b at the second AND gate through this bubbled structure. So here we are getting as output a bar b, and here we are getting as output a b bar. Now we have to sum it, means we have to do the OR operation. So we can put these two as a input of a OR gate, and we can realize y is equal to a bar b plus a b bar. So this is the output for XOR gate. So we can show, and you can see that we can easily realize this XOR gate using just the basic building blocks. Here we could have put this NOT gate. So as I told that AND gate, OR gate and NOT gate, they are the basic building blocks. We can realize any gate using these three gates. So now, and one more thing, where we can use this XOR gate. So they can be used in the arithmetic circuit, arithmetic portion of any computer, and also if we have a comparator circuit where we have to compare two signals, then we can use XOR gate. If we have two signals A and B, if both are equal, then definitely at output we will not be getting anything. That means that output will be off or in zero state. If both are unequal, that is one is in high state and one is in low state, any one of them is in high state and the other is in zero state, then we will be getting output as y. So we can realize which two signals are equal and which two signals are unequal. So using this circuit, this is inequality comparator, we can use XOR gate to compare two signals whether and to see whether they are equal or unequal. XNOR gate, basically it is just a complement of XOR gate. Here the output of two input XNOR gate, we have to see the definition. Here two input, we are talking only in terms of the two inputs, not more than two inputs. The output of a two input XNOR gate is high, means will be in one state if and only if. Here again we have used the mathematical expression if and only if both the inputs are the same. It is just a we can say opposite of the XOR gate where we got a high state when both the inputs were unequal, but here we will be getting high state if both the inputs are identical. So this is the symbol for XNOR gate. It is similar to XOR gate, only we have put here a bubbled structure, that is invert the output of a XOR gate. So this is the truth table for XOR gate. We have inputs A and B, here output Y, we give 0, 0, then means if both the inputs are same, then only we will be getting the output. So we will be getting output corresponding to first row and the last row of the inputs. So here we see this will be 1 and this will be 1, but for unequal inputs we will be getting 0 state. So again we can construct the output using truth table. Here we can see that output, we are getting output at first entry, first row and the last row. So for this, corresponding to this, we will be getting A bar B bar, which is this much, A bar B bar, and corresponding to this we will be getting A and B. So the output will be AB plus A bar B bar, means two AND operation on A and B, and they are the OR operation for these two. So now we can realize again this XNOR gate using the basic gates, which are in fact the AND gate, OR gate and the NOT gate. So we just put A and B at the first AND gate, and A bar B bar, which is through this inverter or through this NOT gate, and we are getting A bar B bar at the output of the second AND gate, and they are implemented to the input of the OR gate, and we will be getting this much, which is the output of a XNOR gate. So now we have studied all about the different gates, that is they are the OR gate, AND gate, NOT gate, XOR gate, XNOR gate, NAND gate and NOR gate. Now as I told in beginning that NAND and NOR gates, they can work as a universal building block. Why? What is the meaning of universal building block? The meaning is we can realize any kind of circuit, not only the gates, but any, if you go further for flip-flops, for the registers, for the counters, any circuit only by using either NAND gates, only NAND gates, or the NOR gates. This is why they are known as the universal building block. So now we will see that how we can realize different gates using only NAND gates and using only NOR gates. So before going to the this NAND and NOR gate as a universal building block, first we should know about the De Morgan's law. There are two De Morgan's law, and they are very important in solving any digital circuit and getting the output, minimizing the output, and means we can do various operations, we will see later. So here we have A, B, C, these are the logical inputs. Logical inputs because they can assume either 0 state or 1 state. We should always remember, we should always keep in mind that A, B, C, they can either be 0 or be 1 in digital electronics and digital systems, in fact in the logic gates, in terms of logic gates. So if we have A, B, C, the complement of the product of input logics. The complement of the product of input logic is equal to the sum of their complements. This is very simple statement. If we have A, B, C, the product of A, B, C, and the complement has to be taken, that will be equal to the sum of their complements, the individual complements. And the second one is the complements of the sum of the logical inputs is equal to the multiplication of their complements. Means if we have A, B, C and there is OR operation on them, and we have to take the complement of the whole A, B, C, D, whatever how many, means it doesn't matter that how much we have the inputs, so that will be equal to the multiplication of their complements, means the AND operation of their complement. Here the multiplication means the AND operation, and the summation means the sum is the OR operation. So now keeping these two laws in mind, now we will be using only NAND gates to realize different other gates. Now first we will discuss NOT. We will find how can we realize NOT gate using NAND gate. It is very simple. As I told that NOT gate has only one input, but NAND gate has at least two inputs. So if we take a NAND gate and we implement A on both the inputs, then output will be equal to A bar. Means this will be so this will work, this NAND, this is the symbol for NAND gate. NAND gate will work as a inverter or as a NOT gate. NAND gate as a AND gate. How can we realize AND gate using just NAND gates? We want to get at output as AB. If we give A and B at this first NAND gate, that will be complemented as a AB bar, and if we have to again take the inverse so that we can get AB. So if we use the second NAND gate as inverter as a NOT gate, then we will be getting output as AB. So it is very easy. How can we use NAND gate as a AND gate? Now how can we use NAND gate as OR gate? Now we want A plus B at the output. Y is equal to A plus B we want. We have to keep in mind that what we want at the output. So y should be equal to A plus B. If we take double bar of both sides, then y double bar will be equal to y, and A plus B ka the whole double bar, the first bar if we use as a De Morgan's law, then that will be A bar, B bar and whole bar. So now we need this A bar, B bar ka whole bar. Then we see A and B as input, means as inverter. So we will be getting A bar, B bar. We just use A bar, B bar, means we will have A bar, B bar as the input, and at the output the complement of A bar, B bar, and which we simplify, then we will be getting A plus B. So this is very easy for OR gate. And if you want to get NOR gate from here, what we have to do? We have just to invert this output y by using NAND gate. So this is very easy. Up to here we have to come to just like OR gate and just implement another NAND gate as the inverter, and we will be getting the NOR gate as the output. So these gates we can realize by using just NAND gate. Now how can we realize XOR gate? So for XOR gate we want at output as a bar B plus AB bar. Again, as I told, that very simple way, take the double bar and simplify it, you will be getting very easily that what kind of, how many gates do you need and how can you give the inputs to different NAND gates. So you see, we have to get A bar and B bar. So we just take, so at the output of third and fourth NAND gate, we will be getting A bar B complement and AB bar complement. And again we implement these two inputs at the input of NAND gate, another NAND gate, fifth NAND gate, we will be getting the output as a XNOR gate. So it is very easy, means this was just to demonstrate how we can realize different gates just by using NAND gate. So we can say, even if we go further, we can realize anything like registers, counters or flip-flops by just using NAND gates. So NAND gate can be used as a universal building block for the different gates. Now again we will see how can we use NOR gate as a universal building block, as a universal gate. Means we have to realize, again I will show how we can realize different gates using NOR gate only. Here if we want to get NOT gate, then we just take a NOR gate and we apply one input at both the inputs of the NOR gate, and we will be getting the complement of that input, that the inverse of that input. So this is very simple, and we can get NOT gate by using this NOR gate. OR gate. Now OR gate means we have to invert the output of first NOR gate by using the second NOR gate. So we have A and B, and the output of the first NOR gate will be A plus B complement, and we again inverse it, make it invert by using NOR gate as a NOT gate. We will be getting y is equal to A plus B, which is simply an OR gate, the function of an OR gate. Now how can we realize AND gate using only NOR gates? So this is the very simple circuit we can see. Here we have A and B as the input, and we want to see AB at the output. Again we simplify it by using De Morgan's theorem, by taking the double bar, means double complement of both sides, and we can see that we can easily construct this circuit. Means all the students are requested to do this exercise by their own. It is very easy, and this is the trick how we can get we can realize different gates using either AND gate or the NOR gate. So we use these two NOR gates as inverter. We are getting A bar and B bar at the outputs, and we apply A bar B bar at the third NOR gate as the input of the third NOR gate, and we will be getting Y is equal to AB. Here we can simplify it also as just by the De Morgan's theorem, using De Morgan's theorem, and we can get A bar A multiplied by B, or the A AND operation on B. So this is simply AND gate. Now if we want to use NOR gate as a NAND gate, what we have to do? We have just simply use this output as a input of the NOT gate. As the input of the NOR gate. Means we have to use one more NOR gate, and we have to apply this output Y as an inverter. This NAND gate you can see. Up to here it is similar to the AND gate. Here we will be getting the output as Y is equal to AB, and if we implement this output at the last NOR gate using it as inverter, we will be getting Y is equal to AB bar, which is the output of a NAND gate. So we could see that how we can use NOR gate, various NOR gates, to realize different other gates. Now XOR gate, how can we realize XOR gate? Again, this is very simple. I have not written detail here. For XOR gate, we need Y is equal to A bar B plus AB bar. Again, if we simplify the circuit by taking the double complement of both sides, we can easily get this circuit. So we have to take A bar, B bar, implement A bar B and AB bar on the third and fourth NOR gate, and now after that we will be getting A bar plus B complement plus A plus B bar complement. If we again use these two inputs as the input of NOR gate, then we will be getting output as the complement of whole these with plus, and then if we again complement it, then we will be getting the output of a XOR gate. Thank you.